And the last talk for today of this room is from Noah Jelich. Yeah? Perfect. He is lead security researcher at Hacken Cybersecurity Services. A little bit shorter the next time, please. And his talk is about something that all the developers fear about it. Testing and coverage. Who uses coverage? One, perfect, yeah. Okay, it's a talk about coverage, but no one uses coverage, right? No, it's
you're in luck because this talk is about.
I think it's. Yeah, I wait. If I think I have to. Okay, perfect.
Test. Okay. So you're in luck, though, because this talk is about how bad coverage is in terms of bad coverage support, which means that you cannot really get good coverage in certain systems, specifically Wasm.
Okay, he says it's bad. Hurrah! Perfect. So the talk is about unveiling WasmCov. Another talk about Wasm. Wasm is everywhere. It's like AI. More later will be AI in Wasm, I think.
There's a whole lot of that if you ask the Google guy.
Revolutionizing this coverage across Wasm ecosystem, but I have another thing to say. You said me one thing before the talk. You haven't learned to whistle until the 20 year of age. Now you can whistle for us.
Okay.
Perfect, you learned, yes! A big round of applause, and the stage is yours, Noah.
Okay, hi everyone, I'm Noah, and yeah, I'll be telling you a little bit about WasmCov, a tool I and a colleague of mine from Hacken made. I have actually left Hacken since. But it's a Apache 2 license, so and it's about solving a whole class of security issues that pop up when developing Wasm in one fell swoop. A little bit about me. Right now I'm a freelance security researcher and full stack developer. At Hacken I've pen tested over 120 blockchain projects, and so far none of those got hacked or had really any serious production mesh issues within the scope that was checked. And I'm really into software testing, like way too much. Like I should be a QA specialist and not a pen tester based on how much I really focus on testing requirements, validation of requirements, mutation testing, fuzzing. But those actually do find security issues when you're, blue teaming the code base. I like Rust, TypeScript. Solidity is something I know, and I'm good at, but I hate. And Python is a solid scripting language for me. I've been coding for a long time. It started honestly with Minecraft modding, and then my dad wouldn't let me play games, so he put a password, and then suddenly I had a USB stick with Linux on it, and there's this thing called, at least there was in Windows XP in 2008, called a SAM file, like a system account management or something like that. And if you deleted it, you could just wipe the password off a computer with physical access, right? So I did that, and I continued playing games, and I really thought about what I was doing. I like good public transfers, so Florence, very, very nice. I especially appreciate the raised pedestrian crossings where pedestrians go level, and the cars have to go over a little speed bump. Those are a nice feature. And yeah, a shout out to Bartosz Barwikowski, who helped out with WasmCov. So, while working at some of the audits at Hacken, I found an interesting set of issues, which I'll be telling you about today. Let's look at some blockchains. Polkadot, Cosm, Wasm, Near, whatever. What do all these have in common? Layer ones, meaning that they're the core blockchains, right? No, not really. Polkadot is more of a framework for creating layer ones, and Cosm Wasm is also a framework. Near is the only real layer one here. They all use Wasm. And how about this? They all use coverage tooling, which allows you to get 100% test coverage score with code that doesn't actually work in production. That's going to be completely and utterly non-functional when running on the actual blockchain VM. How is that possible? Well, let's take Near protocol for example. Well, Rust does have coverage solutions like LLVM or Tarpaulin. I'm sure you heard. They don't apply to Wasm running on the Near VM. Wasm is a very limited runtime. It's still heavily under development, and it just doesn't support, for example, advanced profiling like that. And for instance, you may have smart contracts with payable, right, which means it can receive funds, magic tokens. And that's like a little decorator for functions. And you think they've been thoroughly tested because you wrote some normal Rust tests and you called them and everything worked fine. And you're a developer not really looking at the internals of everything. And you measured the coverage and it came up as 100%. But the grim reality is you were never testing the code that will actually get deployed. The coverage you measured was on x86 runtime. But there are crucial macros in stuff like Wasm bindgen, which simply weren't triggered because they're, conditional compilation, blah, 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 Rust stuff. And the result is you deploy your project, but nobody can call these functions that require authorization, which on Near protocol, for example, uses attached tokens, because those functions require, because those functions can't accept attached funds, because you literally forgot to put the payable macro, because your test suite lied to you and told you everything's fine. And a real world example, a client is going to be adding some integration tests to make sure this doesn't happen again. But this got me thinking, I had to find this issue manually. And I do not like doing that. So what if there was some way to get around this problem? What if there was some way to make sure this never happens again? Like, to anyone. And the solution is simple for all of you except this one guy. It's test coverage, but test coverage that you can trust. We just need test coverage for Wasm. We just need Wasm test coverage. We just need WasmCov, right? But how come there is none? How come nobody solved this before? I mean, Rust has been around for years, and Wasm is used all over the place. So why did nobody solve these layering issues? The answer is that it's really not that easy. And in the meantime, I've spent a lot more time around, like, for example, Wasm Rust working group. So I found out that a lot of tooling is actually sort of getting deprecated all the time and under-supported. And the solution that we found doesn't easily present itself. It requires understanding and digging through compiler internals, which is something that most normal developers won't find themselves doing. They will just put more time into manual QA. But I'm not a normal developer. I'm a guy that's way too into testing, right? So let's talk about compiler internals. Da-da-da-da-da. Rust's compiler is built on top of LLVM, low-level virtual machine, which is just like, a dead name, a bit like GNU means Linux, whatever the thing is, or NPM not being a node package manager. It's one of those jokes at this point. And here's a short LLVM intermezzo. So traditionally, like in this guy's age, probably, you had your C compiler written for x86 runtime, or actually i386 back then, or something. And that was a compiler going straight from source code to the assembly. And each compiler had its own optimization stuff to make sure that code translated well to the assembly. The idea with LLVM is that there is a middle layer. Source code to LLVM to assembly. And it's a much more modular concept. All you need is one assembler, and which does LLVM to assembly for each architecture. So i386 or x86, ARM, or Wasm 32, right? And then you need a front end, yes, a front end for a programming language, which does source code to LLVM. Have you guys ever felt like front-end developers working in your fancy high-level programming languages? Because yeah. And then you can get all the optimizers somewhere in here that are going to work on some intermediate representation of the code, which is like very, very universal. And in order to make a new language, all you need is to write a front-end for a new language, and if you want to make a new architecture like risks, you can just make a new assembler on that side. So it's pretty easy to expand to make new languages and stuff like that. And yes, LLVM is a pretty big tool suite. It has its own coverage tooling like LLVM.cov. But, and of course there are buts, today's society or sexualization, whatever, blah. It doesn't support Wasm binaries. It supports pretty much all other architectures, I mean, all three of them, just not Wasm. And there's a little bit more to that, but it mostly comes to Wasm being a bit young. In short, you can read more detail here, but the workaround needs to happen due to the LLVM.cov map, which is the mapping from source code to like the coverage data that's required by LLVM.conf. It doesn't exist in Wasm. It's just gone for some reason. I haven't gone into Rust internals enough for that yet. And to fix this, we do a little trick. We interrupt at the intermediate representation step. So we take Rust code to IR, as if it's being compiled for the Wasm 32 target, and we just emit that IR with a little Rust flag, and we can play with it a little bit later. And then we let everything continue as it does to Wasm, and we run that Wasm, and that Wasm is going to be run in a special way with profilers, and it's going to actually generate some coverage data. And to map that coverage data that's generated, we actually cross-compile that IR for Wasm to x86, because LLVM.cov does support a normal x86 object file. But this will not work by default because, Wasm doesn't have normal memory management. It has memory size and memory grow, which are Wasm specific. But fortunately, we know low-level assembly, so we can just go back to that assembly and snip whatever we want off, which means just turn all the functions to unreachable, because by pure magic, it still works even if there's no real source code and just function names there. So we do a little regex operation, and we convert the IR to a very minor version of the IR. And then we can run LLVM.cov and get like a coverage report. Oopsie. But there is a lot more. This was just like a single-step workaround, which then still required another about 100 hours to get coverage working for a single project. So while this coverage generation step would allow like a master to generate project coverage for their thing, it's like a Stack Overflow issue with the comment like, never mind, figured it out, here's a simple workaround, and then you're wondering like 2 years later, what the fuck was that guy thinking? It's no path for somebody that's actually just getting into any field. And it doesn't help your average project very much because nobody's gonna spend time on this. And I don't like that. I really like sharing stuff. Like I play mandolin and guitar a bit. So when I find some issues in chords, I go and I make a little pull request on Ultimate Guitar, right? And update everything. So it's just what I like to do. So for this, I wanted to make it something that would work well and that would be easy to use. And for that, I had to take a step back from our client's code, which was blockchain stuff, to the general area, which was Wasm stuff and Wasm problems. And the problems are the same as embedded programming. It's a very limited runtime. You're maybe not even going to have a normal file write I/O. Actually, talking to the Google guy, Wasm just released, so Byte Alliance, the guys that are standardizing Wasm, they just released a standard for file I/O. It didn't exist a month ago for Wasm, so yeah. And with these limited resources, some stuff like a profile or file writes, most people don't know how to work without those. So even if we generate the coverage data, we need a way to get it out. And for Rust, there's a library called minikov, which is a no STD, no profiler runtime way to get stuff out, which just does the profiler directly in there somewhere and allows you to handle the profiler data as you want. And then you can pipe it however you want. In this case, for blockchain, that means either some weird state mutations on chain or logging, like just gigabytes of logs, because that's an option, or just like a custom function actually added to the virtual machine that's running Wasm, which is a very clean solution, but requires more modification. And it took a while, but we did our best. And we actually created the library, which allows you to set up something like this pretty easily. So cargo WasmCov setup sets all the Rust flags and prepares the environment, make sure you're handling all your prof-raw files. Then you just build and run your Wasm tests, and you finalize what generates the report. And that's actually the final product. This is a shorter version of the task because there's a lot of internals, but I've put a lot of QR codes everywhere where you can read more about how it's done. But in short, the Rust flags are a no profile runtime, instrument coverage, and emit LLVM IR to get everything out, plus a bunch of little utility stuff like getting LLVM installed, making sure it's the correct version, that it matches the Rust compiler version. Making sure that the Wasm compiles are handled correctly, because we need to make sure that they're used by tests and that we provide them to tests correctly and that we have a nice interface for that, as well as that they are still within custody of our tool, because we want everything to be automatic and then don't want people to have to write like a long shell script to do this. And this whole thing is also a Rust library that you can just use in Rust code. So it's pretty easy to integrate in like a whole build process. And this is not a Rust specific problem, so this is also valid for writing Wasm in any other language if you want coverage. And we're looking forward to porting this to other languages maybe in the future. But I'm sure you have a lot of questions. Let me first do a little demo, hopefully. And then, so the scripto coverage command, it's like one project that integrated us. It leads to pretty quick generation of a coverage report. And as you can see, it's a standard like Istanbul coverage report. Function line region coverage. You can open, inspect any file. It actually also handles dependency coverage for now. And you can see what needs to be better tested. It has all the standard support of a report, counts, invocations, etc. And this also opens the possibility for future integration with advanced testing tools, like coverage guided fuzzing, anyone? Mutation testing, anything really that relies on coverage and tests passing or not passing properly. So that's more or less the run-through of the tool. For now, it's being integrated by WasmPack, Wasm BindGen, which are major Rust, I mean, they're taking our method. They're not actually taking the source directly for everything. Near Protocol and Radix, which I just demoed. So it's getting some adoption. It's useful, it's needed, but honestly, it should go upstream to LLVM. And I know there's a lot of questions probably in the audience about many different aspects because this was a bit hand-wavy right now. So yeah, on to you guys.
Thank you, Noah. So, questions? Okay. Jogging today. Maybe I feel a little bit.
Hi, I want to ask about this tool. I have an application written in Radix, and yeah, you seem surprised.
I am indeed.
You have indeed, okay, great. And I have some tests of the functions, and you mean that I can use this tool to verify the test coverage?
Yeah. It's
great.
integrated into Scripto coverage.
Oh.
It's still a little bit buggy, but it should provide you
Okay.
valuable input.
So I use only Scripto test.
It's like the actual. It's been added to the main main interface. So you run the normal script. You run Scripto and then coverage, and that's it. And then all the scripts run.
Okay, thank you. Very good.
Okay, just make sure. For now, we need to fix this bug. Make sure LLVM is installed as versioned. So if you just have LLVM cov, right now it's not going to work. You need to make sure it's like LLVM cov 17 or something, depending on your Rust compiler version. So yeah, that's it.
Perfect.
Hi, I have a couple of questions. The first one, if I understood correctly, you are cross-compiling from the LLVM IR to x86-64.
Yeah.
But what if the smart contract platform runs on ARM or RISC? Does it make a difference? I mean, do you have to cross-compile to those
They don't.
ISAs?
I don't think there's any smart contract platform that runs full runtime like that. They're all either very, very customized runtimes written in a specific language, where they need to handle all of their tooling themselves and we cannot help them. Or if they're using Wasm, then they're using one of the many Wasm runtimes, like Wasm Time, Wasmer, Wasm.io, blah, blah, blah. There's like a gazillion of them, like 30. So, and they all have slightly different features. But it's all Wasm in that case, and it has Wasm issues.
Okay. And the other question is, like, would your tool change when Wasm has a garbage collector? Because there is this proposal to have a garbage collector.
I don't think that's going to affect profiling in this way. No, that's
Okay.
like it's going to be part of the profiler, but I doubt they're going to upgrade. Plus, all these runtimes do not support a garbage collector. So but this is not like runtime based. This is compiler level. As you can see, the code never has to run. We are modifying some IR code, cross-compiling it. We're never running it. We're just using it as reference because we're fixing a bug somewhere in LLVM. Because Wasm has...
So in theory, it could be dead code.
It could be that code, yeah. The specific regex that we use is actually just replace every single function body with unreachable, and that's it.
So, other questions? Jogging another time. I'm not so sporty as you can think.
So you said that in general there are a lot of false positives when using other tools, but how do WasmCov behaves in terms of false positives for tests?
So there's no other tools. there's no way to get the coverage. It just isn't supported by the compiler. Like, this is the first tool. It's a workaround. It's not a permanent solution, but you know, until upstream gets fixed, it could be 2 years. I mean, it's been 3-4 months now that this exists, and nothing's really been fixed upstream. So in 2 years, maybe you'll still be using this, you know, if you're unlucky enough.
But as we understood earlier, no one used coverage.
Yeah, so it doesn't matter, you know. You came to the wrong talk. You came for me to tell you how you're a bad programmer, or how you're not using coverage, to warn you about all these issues, and to tell you how I created this awesome tool that's going to allow you to use coverage, just for you to go back home and eat that sweet bowl of, that sweet tub of ice cream that's called not using coverage.
I have a question for the audience. Now, how many of you are going to use coverage?
I know you're lying, okay? I know you're lying.
I think so too, but I still have a hope, a last hope. Tipo, Sanchez, Last Jedi, the last hope. So, other questions? Okay, fine. Thank you. Thank you, Noah. Thank you. Thank you. This is your trophy for the whistle, of course, or only for the whistle, of course. And thank you to be here today.